help us accommodate change. One of the things that is constant to all software. And really, this is, to me, at the heart of it. I mean, if we're going to accommodate this change, then we need to set ourselves up for ways that we can accommodate that change. And one thing that I wanted to talk about was, as far as accommodating change and complexity, there's really two pieces to this. As you decompose a system into its smaller and smaller pieces, you're more able to reuse those pieces, and you're better able to understand those single pieces. And also, those little pieces are much easier to test than the whole system as a whole. Because now that I can focus on the responsibility of the single piece of code, test it, validate that it's correct before I put it into the complete system. That way, I increase the testability and also the flexibility of my code, because now that I've got much smaller pieces and now that I don't have everything integrated. Well, one example that I'd like to show you is, as far as components goes and the way componentry can affect you is probably everyone's seen a motherboard out of a PC. One thing that I find interesting about this motherboard is the video is integrated into the motherboard. So therefore, I cannot test the video on this thing apart from the board itself. You know what I'm saying? Also, if the video goes bad, you know, I guess I could override it, but that's another principle that I'll get into in just a moment. The other thing is that one could see all of the components on this board and think that this thing is very complex, which truly it is. It is very complex. Okay? I mean, you got capacitors, processors, you know, controllers, all kinds of things on this board. But I would say probably the majority of us don't understand all the componentry on this board, but yet probably most of us can put a computer together with one of these. And that's because we don't have to worry about what's inside. All we have to worry about is the interfaces on this guy. It's like abstracted. We've encapsulated all this componentry into a few ports on this side and a few ports here, socket for a CPU and some memory, right? So if we're going to accommodate change and increase the complexity, we need to manage the complexity through abstractions, is really what we need to be able to do. And that goes back into how do we decompose the problem so that we can manage this complexity without having to understand all of the complexity that is there. Another principle that I mentioned is the open-close principle. And as I stated previously, this has onboard video, right? But let's say this video is not very good. We want something better. It won't run our latest game or whatever. Well, obviously, we're not going to get in here and change this board, take components off of it that are soldered on here or whatever, and replace that video card. What we're going to do is we're going to buy a new card that has the capability to do what we want to do, and we'll simply plug it into this component. You see? It simply snap in here. We can turn the onboard off, use the new component. Now then, we've extended the functionality of our PC by plugging in a new component. Basically what that is it is an example of the open-close principle. I can't change this board physically, internally, but I can extend its behavior. It's open for modification, or excuse me, closed for modification, but open for extension, because the ports allow me to extend its functionality. This is a critical concept when we build software. If we design our software in such a way that we can extend it without having to modify it, think how much better we can accommodate change in the future. Okay? That's one aspect. Let me go back to my other slide here. These design principles, though, will help guide us in building this software that is loosely coupled, that is more flexible and easier to accommodate business needs and changes today and into the future. Another thing is that we can use is design patterns. A lot of you heard me talk about design patterns. To me, design patterns are an interesting concept because really they're proven solutions to known problems. They're kind of abstracted so that they fit many different contexts, but in general they are known solutions. I think the design patterns help us out in a number of ways. One, they're an abstraction to a hard problem. If I'm talking to Rob and I say model view controller, He knows exactly what I'm talking about without me having to explain all the details and the inner workings of what that means. He knows what that will accomplish. So number one, design patterns really help us with communication and abstraction, because now I don't have to think about the details. I can just say, oh yeah, model view controller, MVC, or singleton pattern, or factory pattern, or mapper, or gateway, whatever. You've got all these patterns. They're really handles to abstract concepts. The other thing is one of our problems is communication. We have to overcome communication, and I really believe that design patterns help us to communicate. Because now then, if you study design patterns and you know design patterns, and I come to you and say, oh, well, this is simply an implementation of the visitor pattern, you go, okay, I know what you're talking about. We don't have to get into the details of it. The other thing is that design patterns are so well documented on the internet. If, for example, I create a class in my code that says printer factory, well, chances are that's an implementation of a factory pattern. Or I could even add a comment to my code to say, hey, this is an implementation of the factory pattern. I know that that pattern is well documented all over the internet, in books, everything else. So now we've just documented our code by simply using a well-known design pattern. Does that make sense? Again, another tool that we can use is unit testing. And I know you've heard Rob and I talk an awful lot about unit testing. And ironically, Rob was like, whatever, initially. And now then he's like, dude, you're not doing unit testing? Why are you not doing unit testing? Or better yet, test-driven development. What unit testing is, well, really testing is the way we go about validating that we built what we expected to build, or our system behaves in the way we expect it to behave. The problem with testing is if you do it manually, oh, it is just overwhelming to try to test all the possibilities. Also, if we have a mindset that we're going to accommodate change, every time we make a change, we need to test our system again. And if we're going to do that, then what are we going to do? Have 100 people dedicated just to constantly testing our system? That's unrealistic. So I think really what we want to be able to do is we need to be able to write automated tests. We need to be able to use frameworks like InUnit, frameworks like RhinoMox to be able to test our code and to test it in an automated way so that we can rerun these tests and rerun these tests and rerun these tests. So that every time we make a change, we know that we haven't broken something else in our system. Now unit testing is independent really of test-driven development or behavior-driven development. But if you take unit testing to the next level, that's really the direction you're going. And test-driven development is really not about testing so much as it is about design. Again, let me just define test-driven development. Basically, what test-driven development says is I'm going to write a test to validate certain expectations or verify certain expectations. I have no code that makes that test pass. The next thing I'm going to do is once I write my test and set up my expectations, I'm then going to write my code to make that test pass. So now then, I've tested that piece. Well, what that's really done for me too is now then my code exists because I need it in my application. And if you can think about an application as a context, it's running in that context. But by also putting it in a test harness and driving it with tests, that is another context. So you have two contexts here that are different, but yet you're writing your code such that it can function in both contexts. It's not tightly coupled to a single one. You see what I'm saying? So by its very nature, your code becomes reusable. So by doing test-driven development, we're really driving out a better design that's more flexible that will help us to accommodate change. Not only that, we now have, if we do everything test-driven, we will have a suite of tests that cover 100% of our code that we can drive 100% of our code with every time we execute our suite of tests. So every time we make a change, we can rerun these tests.